Well, we came far and long from Battersea, and it's great to see a full room, so we'll start. So Adam, Sheriff, and I would like to first start by thanking you for having us here today because we love to talk about what we do. We're all part of the Applied R&D, a close-knit group at Foster & Partners that is dedicated to cutting-edge research. Having joined Foster & Partners, me and Adam, 18 years ago now, we have worked on hundreds of projects that were very demanding, and we always feel privileged to be in a company that exploits the potential of technology every single day. At Applied R&D, we innovate through disruption and explore the art of the possible today by bringing the technology of the future to the hands of our designers. The company is building in all scales, from furniture to pavilion, yachts, bridges, towers, airports, and even entire cities. And at Foster's, we always strive to change the paradigm of design. And so that's why we at Applied R&D want to look at the technologies that are out there, not necessarily within our own industry, but in industries that are parallel to ours, and try to see how we can use them today in our pipelines and in the way we work. Our team has always been 1% of the company. So currently our company are 2,000 people, and we are less than 20. Our common denominator is that despite our varied backgrounds, we're all accomplished programmers, and we share a passion for innovation and discovery. And that's why ARD has a wide breadth and depth of expertise in different areas. So we do everything from complex designs to performance-driven design, optimization, machine learning, robotics, digital twins, collaborative design tools, XR, you name it, we probably do it. And we have found that what is common as a driver behind all these endeavors that we have is data. Data is the underlying force that drives our decisions and our designs and can help us build better buildings for the future. So that's what we're going to talk to you about today. How by creating, collecting, sharing, and learning from data, we can use data as a driver for our design processes. There is a huge amount of data that is produced during all phases of our pipeline, from design to construction and operation of the built environment. And so we would like to start with design. We have been working on data-driven processes for many, many years, and through the help of technology, we managed to deliver iconic buildings like 30 St. Mary's Axe or the design for the new Mexico City airport that would not have been possible without the use of performance-driven design processes powered by data years back. And with that in mind, I would like to ask Sheriff to speak a little bit about performance-driven design and the processes that drive our designs in the office.
The office's focus on performance-driven design and sustainability inspires a lot of the tools that we develop in-house. Throughout the years, we've done a lot of iterations on those tools that help designers in early stage iterate on design options and be able to get feedback on key insights to take more informed decisions during the design process. The latest iteration that we've been developing is Thalia. Thalia is an early-stage design and analysis tool that brings real-time feedback to all stakeholders. It features an intuitive massing interface that is focused on providing quick design iterations and performance comparisons between the options. Users can assess options using various soft and hard metrics. And one of the hurdles of bringing those metrics in real time while the designers are iterating on their designs was the simulation engines that we're using in the background. And doing this kind of real-time feedback with off-the-shelf tools that are commercially available made that a very hard process. And that led us to start developing our in-house engine. This is where Cyclops comes in. Cyclops allows us to provide real-time feedback on key performance criteria. And it's our own ray tracing-based simulation engine. Initially, 15 years ago, when we started working on this, it was for evaluating views for different seating layouts in stadia. And we were able back then to evaluate around 24 views per minute. Nowadays, we're able to evaluate 600,000 views across an urban block in a minute. And this jump in compute power is powered by the GPUs that we have access to now. This move from CPU to GPU gives us or opens access to orders of magnitude faster analysis. And again, this is all key to providing real-time feedback for the designers. You can see, for example, here a very simple workflow, but not possible with any other tool, where our landscape architects are moving around trees in an urban space and evaluating the performance in terms of sunlight access and views to the river, and being able to take decisions based on that. Or something even more complex, daylight factor analysis. If anyone runs such an analysis, it usually takes minutes, maybe hours. Over here, you can see we're just changing the glass transparency, and we're getting instant feedback. Again, allowing the designers to build their intuition about those performance metrics, and giving them also the ability to create very good analysis models with this fast feedback. We started incorporating a lot of different analyses with Cyclops. Some of them are on the screen, but we also incorporated different ways of creating real-time reports. Because again, a key point is conveying all this information in a well-formatted, standardized way, where designers and other key stakeholders can take decisions and understand what's happening between the different design options. So over here, you can see reports generated for view analysis, landmark visibility, overlooking risk analysis, and all of those reports get generated every time we run any analysis in Cyclops.
So we're talking about data that is provided to the user in real time, and data that is able to drive in real time the decision that we make. But what happens when we scaled up and we look into distributed computing and optimization? There are very interesting things that somebody can do with genetic algorithms, for example. Adam, more than 17 years ago, was working on this project where he has developed a tower using genetic algorithms. The objectives were optimal views to the Petronas Tower in Kuala Lumpur, optimal daylight, and structural stability. But at the end of the day, he gave the objectives and the design aspiration and allowed the computer to produce thousands of options, the final kind of optimized products of which was these towers. So, of course, when we're talking about performance criteria and we're talking about buildings, we have a certain amount of them. But what happens where we're looking at city scale decisions? From investment models to sustainability, there are a lot of drivers that can help us choose how to build a city model. And that's where Hydra comes in. So Hydra is our distributed computing and optimization software platform that is leveraging technologies from cloud-based web development and the movie industry. It supports our entire arsenal of analysis, spanning from environmental criteria to views, connectivity, pedestrian simulation, return of investment, and this kind of arsenal keeps growing. And Hydra, effectively what it does, it harnesses the power of simulation engines, like Cyclops, to turbocharge the creation and analysis of design options in urban scale. That means that we are now capable of creating and analyzing tens of thousands of options, not in a matter of days or weeks, but in a matter of hours. A good example is our master plan for the Guangming transport hub in Shenzhen. And in this case, the genetic algorithms work like that. We had the parcels and we had the design aspirations, and we could decide to say, okay, I'll have to do this and this technology. And we could say, okay, we will spend some time kind of producing options, analyzing them, getting the data, feeding back the data. Instead, we said we're going to do, to allow the computer to do the heavy lifting for us. We're going to give the computer our aspirations in terms of design, and we're going to give particular objectives around areas, daylight, connectivity, and use to the green. And the computer ended up producing
tens of thousands of options with all the relative analysis and bidding their objectives against each other, it had bred better and better solutions, providing us with the pseudo-optimal solution space on a Pareto front, where we were able to identify from the 100 best solutions from these tens of thousands, the different concerns and how the different objectives were bidding against each other, therefore having a data as a major driver, but also producing a lot of data as we're going along. So with these options, creating something like that, that's not the end goal, that's always the starting point of our design exploration. And through other systems, like in this case AI, we have interpolated through these huge data sets and found different ways of helping us understand how our different objectives bid against each other and how these design options end up being created. When we're talking about design and data, we cannot talk about extended reality and how this is going to transform the way we understand data as we design. And we have been taking these things seriously for a long time now. More than 20 years ago, legendary Francis Sage and currently also PhD, honorary PhD, has been working with UCL to develop this. At the time, Francis took headsets that were military grade and cost more than 100K per person. But he managed with UCL to create a collaboration where data was exchanged through an augmented reality interface like that and allowed for people to work together. But you see, at the time, the price was not right and the hardware was not really there. The fact, though, that we have been looking into these things so many years ago means that today we can use these technologies not just as a visualization tool, but as a design collaboration tool and at a fraction of a price. And it has become very, very handy in exploring different types of data as we were working together during COVID, for example, where we were running reviews with different people in their houses, but being able to exchange data information around models, reports, movies, and all the things that we needed to take into consideration. And through these explorations, another product was developed, Glaucon. Glaucon has been our XR product that allows us to be able to do very quickly things like that. So digital mockups, going on site, as we're doing with Tulip, with an iPad and understanding how this building is going to be in its space, and how then that information drives the decisions that we're making. And you can do this, obviously, in different ways with different headsets. And 2 years ago, Franz and I had given a presentation, and he has extensively presented the work around this tool. But more importantly, these types of technologies allow us to not only visualize data and learn from it, but actually be part of the experience. And things like the metaverse are going to be great playgrounds for something like that. I cannot give you too many details, but I can tell you that we're on that space and we're ready to go.
As we've seen with Glaucon, data isn't just numbers and geometry. Sometimes it's the physical reality of the site and surroundings of our designs. For this master plan in Beverly Hills, California, we wanted to understand both the views from the towers towards the surrounding landscape and also how the towers would interact with each other and with existing view corridors. We captured 360-degree panoramic photographs from aerial drones. Using gaming engine technology to display the drone photography as a backdrop, to 3D models of our designs, we created a bespoke application that allowed us to simulate views from each of the residential units across the development. 2 years later, we implemented an updated application that allowed us to include our design with photorealistic HDR lighting and shadows. Viewed on head-mounted display, this made for an incredibly immersive experience of the views from each residence. There is no substitute for data like this, embodying the accurate urban context. We've talked about how important data is in our design process, and now I'm going to look a little bit at just how critical data is in construction. Our design for the Elif Mobility Pavilion for the 2020 Dubai Expo was one of 3 themed pavilions sponsored by the UAE. The inverted trefoil and its sinuous brushed steel louvers shaded the building, which remains after the Expo in a legacy function as part of Dubai's District 2020. It looks astonishingly similar to our vision presented in our competition-winning entry in 2016. Our ability to carefully control data throughout the design and construction is a big part of this successful transition from vision to reality. The base setting out of the building's trefoil design is a fully parametric model based on simple geometric primitives, sheared cones, planar surfaces, and cylinders. Wrapping this facade, we designed the louvers, again using simple geometric primitives of arcs and lines to define each sectional profile. The facade transitions from fully closed louvers to open blades that expose the glass facade with long shading overhangs. Sign functions controlled these transitions to ensure even and tangent continuous curvature. The louver massing couldn't be modeled with sufficient spatial accuracy in our BIM software, so ultimately we delivered the louver model to the client, and in turn the contractor, direct from CAD. Although this CAD model and related documentation provided the source of truth for construction, we still transferred the louver model to BIM with each design iteration through use of our bespoke Hermes software, which I'll be discussing in further detail in just a bit. This transfer allowed for calculating quantity scheduling and other business processes. It paid off again when a variance discovered on site showed that the roof was not going to sit at the correct height, through no fault of our own as a practice. Using this system, we were able to model a design update that would address the deviation and to regenerate the models, facade, and roof package in the course of a day. The result being the beautiful image that you see here. Another pavilion on a smaller scale, the Pavilion of the Holy See, commissioned by the Vatican for the Venice Biennale in 2018. Here we were working not with an ordinary building contractor, but actually the Italian furniture maker, Techno. This became a very unusual design-build exercise, working together with them, constantly adjusting a parametric model as we were reacting to changes discovered on site, and so consistently delivering and redelivering solutions as we had to react to the conditions that arose. Delivering things like a custom clash detection system developed by my colleague Sheriff, and constant updated parametric scheduling of everything from the wooden cladding to the tension members with fastening holes, the angle of which and position of which we're constantly updating in, again, response to conditions as they were being developed in conjunction with a fabricator. The result being, again, what you see here, the image on the left from the opening of the pavilion, the image on the right from 5 years on, where this aspiration of the wooden cladding becoming a sort of trellis to support a greenhouse of sorts having been realized. So obviously, getting data between relevant parties is something that's incredibly important to us through all of these parts of the building, phases of the building life cycle. So I'm going to talk a little bit about our approach to interoperability, which largely is provided by a system we call Hermes. Hermes is developed to address the problem of integrated design. It's really important to have everybody around the table, but traditionally that results in crosstalk. Hermes is a cloud-based server that sits in between all of the disciplines, allowing them to publish their changes as they are required, and then those changes being accessible to all of the relevant disciplines. We used this to great effect on our commission for the Lusail Towers. Is this going to play? Okay, just a moment. Brilliant. We all have encountered, probably, some late-stage design changes, requiring, in some cases, a complete regeneration of a sophisticated parametric model. What Hermes does, in effect, is to connect these parametric models that might be specific to each discipline, so that when the architects issue a new model, structural engineering's wireframes update automatically. Their calculations are conducted without them having to remodel. Those calculations are then published to go with realistic member sizing to, for instance, the environmental engineers, then to the cladding team. Once all of these disciplines have had their say and have a coordinated model, we get a BIM model created effectively for free, accurately representing the contributions of all these other disciplines. We've seen the benefits of managing data through design and construction. Of all the stages of the building life cycle, operation has the greatest potential for generating data because it's where the design vision and its realization as a constructed prototype meet the rich, messy reality of occupancy and climate, of retrofit and renovation. As a practice, we're invested in the promise of digital twins to gather all of this rich data in order that we can use it to understand how our buildings perform in the wild and to inform the simulation of new designs. We're operating a digital twin of our London campus. Starting with a high-fidelity material and spatial model, we add layers of temporal data, including interior and exterior air quality, lighting, energy usage, and occupancy information. Much is made of the opportunity that digital twins offer to facilities managers and asset stakeholders. Our technology stack is focused on providing value to owners, operators, and occupants alike. Our IoT toolkit is the foundation of this digital twin, gathering, storing, and publishing time series data and associating it with the spatial data mentioned earlier. We then expose this data through a variety of interfaces, from widgets on our corporate intranet, to our mobile-first smart campus web application, to our fully immersive 3D campus twin. The campus twin exposes our time series data for interactive exploration and provides multi-level 3D wayfinding that you're not seeing right now. And maybe still aren't seeing, so I'm just going to skip that. Oh yeah, there we are. Interactive exploration of time series data and multi-level 3D wayfinding. It also provides a completely immersive view of our twin, promoting the same opportunities for interactive experience like the metaverse, which Martha described earlier. I mentioned at the outset that the base of our digital twin is a high-fidelity, three-dimensional model. We're actively engaging with 3D laser scanning and photogrammetry as part of our reality capture efforts for XR and digital twins. We were the only architecture practice in the world to participate in the early adopters program for Boston Dynamics Spot Robot. We used Spot both on active construction sites at Battersea Power Station and at our London headquarters. We also employed Spot to capture changes to furniture and other assets within our office space during operations. The promise of autonomous reality capture is to obtain spatial scans regularly in order to complement the data available from ambient sensing. Understanding changes in spatial conditions can inform the understanding of corresponding changes in environmental conditions, energy usage, and occupancy.
From surfacing data for designers to take more informed design decisions, moving to specifying objectives and letting algorithms generate multitude of options and design iterations to learning from the data that we're generating. We've identified different use cases of interest to us where machine learning is of great use, and some of the MVPs that we've been working on, the research we did with Autodesk for creating design assist models that can be suggestive during the design process but incorporate the material behavior. So in here we're looking at thermoactive laminates and how we can flip the design process instead of iterating on different layering mechanisms, applying the heat to the laminated product and then looking at how it behaves, to providing the design that we're interested in and using machine learning models to give us what the layers for the laminates should be. following a simple process of backpropagation using a training data set of input layers and deformed outputs, we are then able to simply flip the process around and provide a model that can sit next to the designer, and every time they decide on a design, the model would provide the input layers for such a thermoactive material. Moving to surrogate models that can replace the actual analytical simulation that is happening. So in here, we're looking at connectivity analysis and visual graph analysis, and again, following a similar process of a curated data set of floor plans from different typologies, running them through the analytical process that usually takes time. So we were, in that case, also leveraging Hydra to parallelize the computation of those outputs, and then training a model to, given a floor plan, be able to provide us with a prediction of what the output of those analyses should be, again, to speed up the way we provide the designers with information in early stage design. We've also been spending time on building an in-house inference engine that allows us to deploy such models and deliver their results directly to the designers in the digital content creation tools that they're using on a daily basis. So over here you can see a plugin that we created in Rhino that basically communicates with the inference API. The inference API decides what the style or the format of the data required from the DCC tool. It applies those transformations to the data, sends it to the cloud where the model is sitting to run inference and return the results of the predictions directly within the tool. Which also is a shift in terms of deploying those analysis models and making sure that everyone across the company is running the latest version of those models. By having such an architecture in place, it's also very easy to start plugging in a sandboxed environment, more recent machine learning models like different image-to-image models, and exploring how designers would be using that in their early stage workflow. So over here, we're seeing stable diffusion running on simple massing models created and getting the results directly through communication with the inference API. Looking also at leveraging some of the more recent advances in natural language processing and large language models, we've been working on building a semantic question answering system on top of some of the design guidelines that we have. So over here you can see someone asking what is the best insulation material to use in a ceiling in X building typology, and they're getting results back with citations from which reference design guideline the resource was, and navigating to the exact page the answer was found in so that they can see it in context. We've also been working on the operational side of the business's data. So we've been collaborating with project management team and looking at a lot of the quotations that we sent out in different projects across the globe, and looking at the possibility of leveraging this data to create predictions of what the quotations should be based on the actuals and trying to minimize the deviation that happens between them. All of this opens up different discussions about how the data should be structured across different teams within the business and how we can start leveraging different tools and technologies to give us such insights.
So we have been talking quite a lot about data and now about AI. I think you were hoping to see quite a few mid-journey kind of images and DALL-E, and these are easy to do. Your grandmother can do this actually if she wanted to, but we kind of need to think how these technologies can really shape the pipelines that we create and how we can use them intelligently to augment our creativity and make us do things that are maintained better and faster. When we're talking about data and when we're talking about AI, we talk about different players that are in the market, right? We know about DeepMind and OpenAI and a lot of new startups that are out there. There is one every 5 minutes. But the biggest player in this game is you. It's the data you produce and the assets you create and the decisions that you make that train these systems. Data has become the currency of the modern society. It is in many ways the most abundantly generated product of the 21st century. And every single action in your life is underscored by the production of data that is being mined and used in a variety of ways. In our industry, we just showcased 3 different ways by which data is driving our decisions. So we have the bottom-up approach, where data is created in real time as you design, and it kind of leads to performance-driven design solutions that are driven bottom-up through data visualization and augmentation of your intuition. We had a top-down approach, more like the use of genetic algorithms that can create huge data sets from which you can start understanding how the different levels of data can leverage a better design solution. And then finally, we had the data training the machine, in which case we have been starting to create cognitive machines that not only mimic what we do, but can actually and will very shortly be able to generate new scientific knowledge and perform potentially any tasks humans do. And the message that I would like to take out there is that to harness AI's power and the power of these tools, we first need to be able to control what powers these tools, and that is data. All these technologies are empowered by data, and they have the potential of augmenting our creativity and our problem-solving capacity. So, no matter the size of the company we're talking about, the industry is already or should already be looking into achieving a systematic collection and classification of data sets in all scales and stages of the design process, from layouts to cities and from concept to operation. The question is how to collect, organize, and process data across disciplines in a meaningful manner so that ultimately we know how to leverage it for future projects. Oppenheimer said, "Technology happens because it is possible." So let's drive the technological revolution that is coming by controlling what fuels it, data. Thank you very much.